So let's continue with part 2 of section 11.2, still working with series. Let's take a look at this example to find the value of a series here as n goes from 0 to infinity of 1 over the quantity n plus 1 times the quantity n plus 2. Well, if you recognize this, if we put an integral in front of it, we would have to do what technique? Partial fractions. See, this stuff never goes away. All right, so what we're going to take a look at here is we're just going to focus on the fraction here. So we're going to say 1 over the quantity n plus 1 times the quantity n plus 2 is going to equal a over n plus 1 plus b over n plus 2. And we'll solve for a and b. So now we'll have a times the quantity n plus 2 plus b times the quantity n plus 1 is going to equal 1. Let's let n equal negative 2. That means a is going to go away, and then we're going to get a negative 2 plus 1, so we'll get a negative b is equal to 1, therefore b is equal to negative 1. Then let's let n equal a negative 1, then the b is going to go away, and then we'll get a negative 1 plus 2, so that's going to give us a is equal to 1. So now we can say that the summation, as n goes from 0 to infinity, of 1 over this, becomes a summation as n goes from 0 to infinity of a, so we'll have 1 over n plus 1, and then we'll get a minus 1, so we'll just say minus 1 over n plus 2. So what we're going to do is just start to write out some of the values here. So if n is 0, we're first going to get a 1 over 1, so we'll get a 1 minus a 1/2, and I want to kind of keep that together here. Then we'll get, if n is 1, we're going to get a 1/2 minus a 1/3. And let's continue this out a few more times. Next, if n is 2, we're going to get a 1/3 minus a 1/4. Then we should get a 1/4 plus a 1/4 minus a 1/5, and so on. So what's happening here is, if you notice, if we started to add these, notice this second term of the first quantity is the opposite of the first term of the next one. So those are going to cancel. Same thing here, and it's just going to keep happening. So everything's going to keep canceling as we keep going, and we're just left with a 1. And when this happens, when we start to write things out and they start to cancel, whether they're right next to each other or somewhere down the road and they cancel out, we call this a telescoping sum. So we'll practice another one, not necessarily using the partial fractions, but just to get some more use with or work with a telescoping sum. So let's say the partial fractions portion was already done for us, and we have the sum as n goes from 1 to infinity of 2 over n minus 2 over n plus 3. So again, just start to write this out. If n is 1, we're going to get a 2, and then we're going to get a minus 2 over 4, so we'll see minus 2/4, plus, if n is 2, we'll get a 2 over 2, we could just leave it like this, minus 2/5, plus, so it doesn't look like anything's crossing out just yet, so we just got to keep going with this and sort of trust the problem. So if n is 3, we're going to get 2/3 minus 2/6. And we'll get, if n is 4, we'll get a 2/4. Now we have something all the way up here, minus a 2/4 and then a plus a 2/4. And then we'll get minus 2/7. Let's keep going a little further. We'll continue this down here. So next we'll get a 2/5 minus a 2/8. Now it starts to look like it's canceling out. And we'll do this one more time. Then we'll get a plus 2/6 minus a 2/9. and so on. So yes, this 2/4 we'll cross out with this 2/4 over here. The 2/5 here we'll cross out with this one, then 2/6. So as we keep building, we'll get a 2/7, which will eventually cross out with this. We'll get a 2/8, which will eventually cross out, and a 2/9, and keep going. So what we're left with first here is a 2 plus a 2/2, which is 1, plus a 2/3. So we're going to get 3 plus 2/3, which is 9/3, plus 2/3, which gives us 11/3. So just some more practice with exploring a telescoping sum. All right, another example kind of takes us to a specific type of series called a harmonic series, and we're going to show that the harmonic series is divergent. So this is the series, and written out, if n is 1, we get a 1. If n is 2, we get a 1/2, then a 1/3, then a 1/4, and so on. We want to show that this is divergent. So we're going to start by writing out quite a few of these terms. So I'm just going to continue this down here. We'll say that the series again is 1 plus 1/2 plus 1/3 plus 1/4. I'm actually going to write this out to 1/16. And then it does keep going. All right, so what we're going to do is we're going to kind of compare this to a certain value. So I'm still going to leave the 1 plus the 1/2 right here. But if I look at these two values, 1/3, which is larger than 1/4, so the sum of these two is going to be greater than 2 times 1/4. So imagine if I just had 1/4 plus 1/4, that's 2 times 1/4, which is 1/2. So I know this sum is going to be greater than 1/2. Then I'm going to take a look at 1/5 all the way up to 1/8. This sum is going to be greater than, because 1/5, 1/6, and 1/7 are all greater than 1/8, the sum of these four fractions is going to be greater than 4 times 1/8, which is also 1/2. Then if I added the rest of these together, 1/9 all the way to 1/16, 1/9 through 1/15 is greater than 1/16. I should have 8 of these. So this is going to be greater than 8 times 1/16, which is 1/2. So I know that the sum of this series is going to be greater than the 1 plus the 1/2 plus this 1/2 plus this 1/2 plus this 1/2. And then I could take another set of fractions and add them together, and that would be greater than another 1/2. So then this keeps going. And slowly but surely it is increasing, so it will keep increasing without bound. Therefore, the harmonic series is divergent. Now there could be variations of this, so let's take a look at an example, another example. So we're going to answer convergent or divergent. Start with 1/6 plus 1/12 plus 1/18 plus 1/24, and so on. So the trick is to be able to write this using sigma notation. So we could say this is the summation of n equals 1 to infinity. So if we take a look at the pattern amongst the denominators here, we could say it's 1 over, and the first one looks like, maybe we could say 6 times 1, and then 6 times 2, 6 times 3, so we could say 6n. Now notice, because it has the 1 over n, it is connected to the harmonic series, and we could factor out a 1/6. We could say it's 1/6 times the summation as n goes from 1 to infinity of 1 over n. So this is divergent because this right here is still the harmonic series, but it's a constant multiple. So this is a constant multiple of the harmonic series, which still makes it divergent. All right, so let's take a look at a theorem. So if the series So if we're looking at this series here and it's convergent, then the limit as n approaches infinity of the sequence here is going to equal 0. Now this doesn't work the other way around. Just because a limit might be 0 doesn't mean the series is convergent, and that harmonic series is a prime example. So in other words, this is saying the sequence of the terms must go to 0. If they don't, then there's no way the sum will be finite. So we're going to take a look at a test for divergence. So if the limit of the terms is not 0, meaning this notation right here, then the series is divergent. I'll take a look at two examples. All right, so this series we'll say first is divergent, and then we'll take a look at why. Because if we were to look at the limit as n approaches infinity of n over 3n plus 1, again, we can just divide every term up here by n. So if we did that, we would get 1 at the top, 3 in our denominator, and then 1 over n would just go to 0. So this is equal to 1/3, not 0. Remember, anytime we see a -1 to an n, that's an alternating series in this case, or sequence if we were to write out all the terms, but this is also divergent. Since the limit, as n increases without bound of -1 to the n, is not 0 because it keeps bouncing between -1 and 1. All right, and then to wrap up this section, we're just going to take a look at some properties of series. So if we have the series of the summation of a sub n and the summation of b sub n, so if these two series are convergent, then so are the following. The summation of a constant c times either one of those. So we'll say where c is a constant. And the summation of the sum or difference of the series. And let's see how we can use this to help us out. So our last example, let's go ahead and calculate the sum of the series here. So we have two different series that we're going to take a look at. So first we're going to take a look at using the second property here. We'll just do the summation as n equals 1 to infinity of 8 over n times n plus 1. This could be rewritten as taking the 8 out in front. That's the constant as well, of 1 over n times n plus 1. Now kind of skipping ahead, but we would use partial fractions technique here. This would become 8 times the summation as n goes from 1 to infinity of 1 over n plus 1 over n plus 1. So in this case, a and b would both be 1 if we did the work for it. So we'll just say by partial fractions. So this becomes a telescoping sum. So what's going to happen is if n is 1, we're going to get a 1 plus 1/2, and then we'll get a let's think about that. That should be a minus here then. B would end up being a -1. So this would be a telescoping sum because we would get a 1 minus a 1/2, then we get a plus a 1/2 minus a 1/3, and so on. So the only part that would be left that would not cancel would be that first term. So this becomes 8 times 1, which is 8 since it telescopes. All right, then we'll take a look at the second one. We would have 1 over 7 to the n minus 1. This is a geometric series because we could write this as the summation. We could say a is going to be 1 because if n is 1, we're going to get 1 over 7 to the 0 power, which is 1. So in this case, a is 1. And then we could say it's just 1/7 to the n minus 1. So r is 1/7. So this is geometric. And then we could say the sum of this is going to be a, which is 1 over 1 minus r. So 1 minus 1/7, which becomes 1 over 7/7 minus 1/7 is 6/7. So then we get 7/6. So we're just going to add these two together. So then the summation as n goes from 1 to infinity of 8 over n times n plus 1 over 7 to the n minus 1 is equal to 8 plus 7/6.